just a quick review. We started. Thank you. We started to design steel beams. Steel beam or beam in steel is more easy than beams in concrete. Just we are using tables to design. Your ultimate moment from structure analysis results must be smaller than or equal. Put it in your mind. For any design, we have two sides. The first one, ultimate applied load, coming from external load, from structure analysis, which equal 1.2 dead load plus 1.6 live load. This is the simplest combination. Maybe this is M ultimate, maybe this is P ultimate, whatever, from external load, from structure analysis. This applied load must be smaller than or equal your design capacity. Maybe your design capacity for tension member called design tensile strength. For column or compression member, design compressive strength. For beam, design bending strength. Design bending strength. All of them the same philosophy. Your applied load, factor applied load must be smaller than or equal your design strength. Design tensile strength in tension member, design compressive strength in compression members and columns, design bending strength for design of beam. The most simply method, your design moment equal, or your nominal moment first equal plastic moment equal F yield times Zx. Zx is a section properties, you can get it from a table. Is a plastic section modulus about the x-axis. Based on what is the name of your cross section, you can figure out what is the value of Zx. F yield based on what type of steel. To convert your nominal strength to design strength, we are using a factor called resistance factor for building, Phi bending equal 0.9. And last time we explained how this equation M plastic equal F yield Z coming from, if you have bending moment, we have tension in one side, compression on the other side. In between, we have something called neutral axis. Your cross section is symmetric. That means your neutral axis admit height. So this distance will be h divided 2. This distance will be h divided 2. This area of cross section will be a divided 2. This area of your cross section will be a divided 2. The upper area of your cross section under compression, compressive force equivalent to this compression stress equal C equal A compression time F yield, and the lower part of your cross section under tension, so we have tensile force T from equilibrium C equal T. If you take moment at this one and the distance in between equal A, you can figure out what is the plastic moment. One more time, your plastic moment is your nominal moment. If you would like to get your design moment, you need to multiply it by Phi. We covered this example last time. We talked also about classification of cross section. Your cross section may be compact. We like compact cross section. Compact cross section means you will get the full capacity of your member. Non-compact, it's not bad and not good. In between. Slender cross section, it's not good. We can expect and desired mode of failure. To classify your cross section, we have a value called lambda for flange equal T flange divided to T flange. Here is your cross section for W shape or for channel. This term or this part of your cross section called flange. Width, this flange called B flange. Thickness called T flange. This part called web. It is your H total height. It is your T web thickness. For a channel, it is your flange. So we have B flange, T flange, and we have H, and we have T web. So we need to classify first what is the classification of your flange based on lambda, lambda P, lambda R. If lambda smaller than or equal lambda P, your cross section is compact. In between lambda P and lambda R, non-compact. Greater than lambda R, slender. The same will be done for web. And your question last time, if we have web is compact and your flange non-compact, then your cross section finally will be non-compact. So if the web is compact and the flange is non-compact, the shape is classified as non-compact based on the worst classification. Last time also we talked about very important phenomena in steel structure, which called lateral torsional buckling. Anybody remember which part in your beam is under the effect of lateral torsional buckling? Which part? Remember. This word buckling means something under what? Tension or compression? Compression, perfect. So if you are talking in concrete or in steel, what type of material, I don't care. If you are talking about something called buckling, means something under compression. So this part which is under compression is expected to buckle. So your beam, in one side we have tension, on the other side we have compression, and in between we have something called neutral axis. That's right? So the only part expected to buckle is the compression flange. This flange. Your flange as a whole element will be laterally deflect. Laterally move laterally and twist at the same time. So we said lateral torsional buckling. Lateral movement and twisting. Torsional. So this phenomena happens for an supported compression flange. And supported compression flange. I'm sorry, what you mean by unsupported? Can you watch this bridge? This bridge, we have beam, 4 beams. Which part in tension and which part in compression? We have here support. We have another support here. So the beam in between is simply supported. So this flange under tension. the top flange under compression. You applied cross bracing. This cross is repeated at interval. The distance between each cross, this one, and the following one, and the following one, the distance in between, called an supported compression flange. This length called LP. In this case, your beam is supported here, your beam is supported here, and free in between. So your unsupported length, LB, is this distance. We don't like to make this distance large and large. Larger unsupported lengths, we can expect lateral torsional buckling will happen. I would like you to understand the phenomena, this phenomena. We will learn how to solve, that's fine. But this phenomenon is important for steel structure. We have very undesired mode of failure, which called lateral torsion buckling, because you were part of your beam under compression. So the beam can support more load, maybe higher and higher, but this undesired mode of failure make limitation on the applied load. We don't like this mode of failure. Any questions so far? So LB and supported lengths. As you see here, we have cross bracing. This cross bracing will make support for the top flange to the bottom flange. My issue with the top flange, this cross bracing is repeated here and here and here. The distance in between called unsupported length of your compression flange. I have question. What will happen if you have beam looks like this, and this beam is supported or connected or working in composite with concrete deck with the shear connector or whatever. That is your cross section. Can you tell me what is your unsupported length? This flange under tension. Because we expect a moment like this. In between we have something called neutral axis, so this part under tension and this upper part under compression. So this flange will be under compression. Can you tell me what is the unsupported length LB? Here, your unsupported length between this point and the following point and the following point and the following point for each cross bracing. So here is your LB, unsupported length. But here your beam is composite with concrete deck. So your top flange is connected to concrete at each millimeter, at each 100 of millimeter. So your unsupported length equal 0. Every inch in your flange is supported with another element, which is concrete flange or concrete slab. So sometimes, if you don't have concrete, we need something else to make support, like bracing. Sometimes we have concrete deck on the beam, so your support or the unsupported length equals 0, continuous support. Anyway, So we have three modes of failure. The first one, the beam or the cross section will be yielding for the whole cross section. This is only for compact section. You get the full capacity of your cross section, nothing waste, and your nominal moment equal M plastic. Sometimes we have lateral torsion and buckling, which is considered overall beam instability for non-compact section. Actually, we didn't get the full capacity of your cross section. Your cross section can support more load, but this phenomena limited your design. The third one, which called instability, is local instability. Only small part of your flange unstable. We have local buckling. This is only for cylinder section. We don't like this type of cross section. First one, compact section, your cross section is perfect, so your plastic moment equal F yield Z. You can add here a term phi, bending equal 0.9 to get your design. We covered all of this material last time. The new thing for today, if your LB greater than LP, smaller than LR. I'm sorry, wait a moment. What you mean by LB? This one. What do you mean by this term? LB called the length between points that are either braced against lateral displacement of the compression flange or braced against twist of the cross section. As you see in the previous example, this one, we have vertical bracing. This bracing